We'll just wait for a couple of more minutes and then we'll start. So let's start. Uh, Hello everyone, this is Tanya. I'm one of the TAs assigned to the aircraft design course taught by Professor A.K. Ghosh. So today we'll go over the questions of week 8 and then some questions that will help you with the week 9 assignments. So we'll just go over the concepts that will help you even with the week 10's assignments. Okay, so let's start with the questions first. This is a question that we have done I think a couple of times before and the last of the one week before that. If thrust to weight ratio T by W of an aircraft is 0.1 and the aerodynamic efficiency is 10, what is the approach angle of the aircraft? So it's very simple. We'll just take sine of the approach angle is D by L minus T by W, which is 1 by L by D minus T by W. So we get 1 by 10 minus 0.1, which is 0. So the approach angle in this case is 0. Okay. So next question. With the increase in equivalent airspeed, the static stability of an aircraft will. The static stability of the aircraft depends on factors like, so the only criteria is Cm alpha should be less than 0. So the aircraft's speed does not come into play in this relation, right? So the equivalent airspeed does not affect the stability in any way. So it remains constant. Okay. Next. For an aircraft, the stall velocity for cruise is 100 meter per second and during a maneuver, the load factor is 9. What will the stall velocity during maneuver be? So the equation for stall velocity, we've been seeing this from first lecture, is under root of 2W by S by rho CL max. Now this is given as 100. So let this be the first stall velocity. Now the second stall velocity, so this was under the assumption that lift equals weight. Now when lift equals n times weight, you have under root 2W by S n by rho CL max. And that is nothing but under root of n into Vs1. So that's under root 9 into Vs1, which is 300 meter per second. Alright. Okay. Next question. The drag polar of a piston engine powered aircraft is given by CD is 0.03 plus 0.03 CL square. What is the lift coefficient, maximum lift coefficient at maximum lift to drag ratio? So this we had seen in the first few weeks. So CL at L by D max is given by under root CD naught by K. This is CD naught and this is K. So in this case it will be under root of 0.03 by 0.03, which is 1. That's that. The total pitching moment coefficient of an aircraft is given by Cm equals 0.02 minus 0.8 alpha, where alpha is the angle of attack. The aircraft trim alpha in degrees will be. Trim is what? When the sum of forces and moments is 0. Okay, so in this case, when the pitching moment is 0. So it will be Cm equals Cm naught plus Cm alpha into alpha equals 0. So Cm naught is 0.02 minus 0.8 into alpha trim is 0, and so alpha trim will be 0.02 by 0.8. What is this value? It comes to 0.025, and that's in radians, and they've asked you in degrees. So convert it and you'll get 1.43 degrees. So that's the answer. Okay. Now let's revise some of the stability concepts. Alright. So the equation for pitching moment coefficient, which you've seen multiple times, is Cm naught plus dCm by d alpha into alpha. And the only criteria necessary for static longitudinal stability is that Cm alpha should be less than 0. Right, that is the only criteria. This one. Then another condition that we've seen is that Cm naught should be greater than 0. It is not a criteria for the static stability. It is only a preferable condition that we require, that is to trim the aircraft at positive angles of attack. Alright, so if you have, this is Cm versus alpha, you have two slopes. So this is A and B. So here the Cm naught is positive and here it is negative. In the case A, you trim the aircraft at positive angle of attack. In case B, you trim the aircraft at negative angle of attack, which is not generally desired. So we require Cm naught to be greater than 0 only to trim the aircraft at a positive angle of attack, and it is in no way related to stability. Alright, then we looked into the wing and tail contributions towards this pitching moment coefficient. So the wing coefficient has two components, tail contribution has two components. So this is the Cm naught contribution by the wing. This entire thing is the Cm alpha contribution by the wing. This is the Cm naught contribution of the tail, and this entire thing, including the negative sign, is the Cm alpha contribution of the tail. Okay, so now you can see that we require Cm alpha to be less than 0. Now if you look at the wing contribution of Cm alpha, Cl alpha is positive and xcg minus xacw is a positive quantity. So Cm alpha of the wing is positive. So it does not contribute towards static longitudinal stability. So what component contributes towards it? Tail. Now let's look at the tail individual parameters there. VH, tail volume ratio, it's positive. Tail efficiency factor, it's positive. What is tail efficiency factor? Eta. Do you know what it is? What is it equal to? VH is horizontal tail volume ratio, ST LT upon SC bar. What about efficiency factor? So efficiency factor is the ratio of the velocity seen at the tail and the free stream velocity square. Okay, so this is your tail efficiency factor, horizontal tail efficiency factor. Again, it's a positive quantity. Cl alpha tail positive. This term is positive. So if the minus sign were not there, the contribution of tail towards static stability would also be positive, which is why you have this negative sign here. Okay, so the tail contributes towards stability, towards horizontal longitudinal stability. All right. Okay. So these are the wing and tail contributions. How do we ensure Cm naught to be greater than 0? We have said that we prefer Cm naught to be greater than 0. What, by looking at these equations, what can you suggest? How do we make Cm naught greater than 0? In what ways can we make Cm naught greater than 0? Just look at the equations. Look at the equations of Cm naught wing, Cm naught tail, and then try telling me what could make it positive. Because this term right here, this is negative, right? Cm AC wing is generally also negative. What could make it positive? Yeah, what in the tail? What part of the tail? How do you make it positive? You can play around with the tail setting angle, right? You can play around with the tail setting angle. Yes, negative angle of attack, and then you get Cm naught to be positive. So that's one way. Another way is to make the Cm AC wing also positive. How do we do that? With a reflex airfoil, right? So reflex airfoil and playing around with the tail setting angle, these two will help you to ensure that Cm naught is greater than 0. Okay. Then we looked into neutral point. Neutral point is nothing but the aerodynamic center of the entire wing, of the entire aircraft. Okay, so it is analogous to the aerodynamic center. So it is a point at which the Cm alpha or the pitching moment does not vary with angle of attack. Cm alpha is 0. So we saw the equations for neutral point, and then we saw static margin. Static margin is a quantitative is a quantity that gives you a feel of the stability. So more positive the static margin, more stable the aircraft is. So for a stable aircraft, dCm by d alpha or dCm by dCl will be negative, right? So the negative of the slope is the static margin. So the static margin will be positive for a stable aircraft, right? That also means that the neutral point is ahead of the CG, which is what is required. So static margin gives you a quantity to tell you how stable the aircraft is. So more the numerical value of the static margin, more is the stability of the aircraft. And these are a few formulae that we had looked into. This will help you in the questions. We'll just go over it. So horizontal tail volume ratio we know, right? ST LT upon SC. And what is this LT? It's the moment arm of the tail. So that is given by the distance between the CG and the aerodynamic center of the tail. Then we looked into downwash. So what is downwash? Is epsilon naught plus the epsilon by the alpha into alpha. This is alpha wing, okay? Let's be clear about that. So this is alpha wing, right? So in this, the epsilon naught and the epsilon by d alpha are given by these two equations. Another thing that we've seen is the difference between the CL alpha of a 2D airfoil and 3D wing. Okay, so the difference is that one is so airfoil is a wing of infinite span, right? For 3D wing, it is a finite span. What happens is that the flow interacts in the boundaries and there is a reduction in the CL that the airfoil could have produced. So that is given by this formula. Now, the thing that you need to remember here, the important thing that you need to remember in all of these formulae is that they are all valid only in radians or per radians, all in terms of radians. So the CL alpha 2D has to be in per radians. The value that this equation gives will be in radians. So on either side of the equation, they are dealt with in radians, per radians, all in terms of radians. So this is something that you need to remember. Alright. Then we moved into control. This is in the longitudinal sense, okay? So what does control do? Control enables us to trim the aircraft at different CL values. So what it does is, it does not change the stability, okay? So this, I think, question is asked multiple times in your assignments. So changing any control surface or deflecting any control surface does not affect the stability in any way, okay? Stability depends upon the other properties that we've seen now, the contributions of wing and tail. In none of these equations did the term control come. None of the control surfaces appeared in those equations. So what we need to remember is that control surfaces do not affect stability in any way. What does it do? So if this is your Cm versus alpha or Cm versus Cl, either way, let's take Cm versus Cl, alright? So this was your graph. Now if I change the slope of this, it changes the stability. But the control surfaces do not change the slope of the graph. What do? They translate this graph. So I can move it here, I can move it here to change the different CL trims. These are the CL trims, right? So if I want to change, if this was my CL trim 1, initial CL trim, but now I want to trim it at this CL trim. And then I deflect the control surfaces. So deflecting the control, okay, here although it looks like, let me just rectify that, the slope doesn't change, alright? Okay, and this is CL. So the slope doesn't change when you deflect the control surfaces. Control surfaces do not affect stability in any way, okay? They only translate the graph, okay? Yeah, so the conventions are, when you deflect the elevator down, it's a positive deflection, it's considered positive deflection. So what happens is that it gives you an effective camber, right? You have, if this was your tail is usually symmetric, let's do it like this. So if you deflect the elevator downwards, if you deflect it like this, what happens is that it introduces a camber. Effectively, there is a camber that is introduced, right? So then what happens, we've seen from our lift curve slopes that in introduction of a camber, increases the lift generation. So there is lift even at zero angle of attack, which is what's written here. Okay, so these are some formulae related to CL delta E, CM delta E, how much the lift and the pitching moment vary when the elevator is deflected. Downward deflection of elevator is considered positive. When you deflect the elevator down, it produces an increase in lift. So delta L. So if this is your fuselage reference line, this is your CG, it produces a pitch down. So deflecting elevator down is positive, produces positive lift. You can see here that it produces a positive lift, but it produces a pitch down moment, which is why there is a negative sign here. Alright? Okay. Then delta E trim, that is the amount of elevator to deflect the elevator, amount of elevator that needs to be deflected to trim at a given CL trim. Alright? So when that CL trim is given to you, you plug it into this formula and then you know how much you should deflect your elevator. Okay, now let's move into some questions. An aircraft is having a rectangular wing of wingspan 3.5 meters. So you have B is 3.5 meters, chord is 0.25 meters, horizontal tail volume ratio is 0.57, so VH is 0.57. What should be the length of the tail arm if the aircraft assume tail area is 25% of wing area? They've asked you to find out this. Try doing it, take a couple of minutes, try doing it, and then we'll do it together. Okay, so this is fairly simple. We have done this formula multiple times. So it's VH is ST LT by S wing C bar. They've asked you to find out LT. So LT is VH S wing by ST into C bar. Now VH is given to you as 0.57. Assume tail area is 25% of wing area, so it's 1 by 0.25 and C bar is 0.25. So the answer is 0.57. This was fairly simple. So the moment arm, the tail moment arm is 0.57 meters. Okay. The aerodynamic center of the horizontal tail from reference line is 1.11 meter. It hasn't loaded. Okay, yeah. The aerodynamic center of the horizontal tail from reference line is 1.11 meter. Tail arm distance is 0.68 meter. What is the location of center of gravity of the whole aircraft from reference line? So let's try drawing this. So take some reference line. So this is the fuselage reference line. So this is where your wing is. Usually our reference line is the leading edge of the wing, but it can be any position. Then you have the tail. Okay. Now they said the aerodynamic center of the horizontal tail from reference line is 1.11 meter. So if this is your aerodynamic center, this is 1.11 meter. Tail arm distance is 0.68 meter. So tail arm distance is distance between what two points? CG and AC tail. Perfect. So if I take CG somewhere here, so this distance is 0.68 meters, right? 0.68 meters. Now they've asked you to find the location of center of gravity from the reference line. So this is the question mark. That's XCG. So XCG would be what? It would just be 1.11 minus 0.68, right? Very simple. 1.11 minus 0.68 gives you 0.43 meters. Correct? Very simple. Let's go to the next one. What will the value of Cm naught? What will be the value of Cm naught be if CL? Okay, so there's a mistake here. This should be CL naught. Okay, yeah. What will be the value of Cm naught at CL naught equals 0.22 for an aircraft flying at CL trim 0.66 and static margin of 10%? Okay, so just read this question carefully. It is slightly tricky, but just try doing it. So let's just write down CL trim is given to you, CL naught is given to you, static margin. So that means static margin is minus dCm by dCl, which is given as 10%. Correct? So just try doing it, then we'll try doing it. Okay, just try doing it. Okay, 0.44. Okay, let's try doing this. So one thing that we need to know is the difference between Cm naught uh, that we have defined earlier on and the Cm naught in this case. Okay, so two equations that we have. One is Cm pitching moment equation that we've studied here, Cm naught plus Cm alpha into alpha. This is the Cm naught that we have learned. But in this question, that you can see that they've given the relation between Cm and Cl. So there you have Cm is some Cm naught, let's call it Cm naught 2 plus dCm by dCl into Cl, right? So you have two graphs. One is, one is Cm versus alpha, and the other is Cm versus Cl. Although both of them follow the same pattern, same trend, this Cm naught value need not be the same. So this is Cm naught that we have learned that from the equations, and this is the Cm naught 2. So in this question they've asked you to find Cm naught while the relation given to you is between Cm and Cl. So they've actually asked you to find out this Cm naught 2. Okay, so now if we expand this equation, if I were to write Cm naught 2 plus dCm by dCl into Cl, so that is dCm by dCl Cl naught plus Cl alpha into alpha, and then I write Cm naught 2 plus dCm by dCl into Cl naught plus dCm by dCl into Cl alpha into alpha. Okay, so now this is similar to the first equation, right? Okay, so they've asked you to find out Cm naught. So I think I made a mistake while saying that. They've asked you to find out Cm naught. Cm naught is this whole thing. This is Cm naught, correct? It's not the intercept between the Cm versus Cl graph. That is Cm naught 2, that's some other quantity. The Cm naught, the nomenclature that we have studied, is the Cm naught between Cm and alpha. So now our Cm naught is this quantity, okay? So now let's try finding out all of these terms. That we need to find out Cm naught 2, that is this intercept of that graph. dCm by dCl we have, Cl naught we have. Okay, so we just have to find out Cm naught 2. How do we find that out? Now let's take we need to find out this intercept point, right? So you just take the slope between 2 points and find out the unknown quantity. So let's take this as 0.1 and this is 0.2. So dCm by dCl will be Cm2 minus Cm1 by Cl2 minus Cl1. So that is Cm2. The Cm at 0.2 is 0 minus Cm at 0.1 is Cm naught 2. Cl at 0.2 is Cl trim, which is given in the question, minus Cl at 0.1 is 0. So from this equation, if you were to rearrange, you will get Cm naught is Cm naught 2 would be dCm by dCl is, you just calculate this value and you get 0.066. Okay, so then you plug it into this equation. So Cm naught is Cm naught 2 plus dCm by dCl into Cl naught. So that is 0.066 plus dCm by dCl is, where is it? Yeah, it's 0.1, it's minus of 0.1 into Cl naught is 0.22, and then you get 0.044. You got the right answer, correct? Okay, let's go to the next question. X bar NP is given by, so we had done a derivation where we derived the X neutral point, like the equation for the neutral point, right? Here some new terms are there that we have not seen before, that is Cm alpha of the fuselage, F here is fuselage, and Cl alpha of the wing. So one thing that you can use to remember this, so static margin, take static margin is x bar np minus x bar cg. Static margin is also minus of dcm upon dcl. So you get minus dcm by dcl. Now this is usually written by dcm upon dcl of individual components. So you can do dcm by dcl of the wing minus dcm by dcl of the tail minus dcm by dcl of the fuselage, so on and so forth. From this equation you can try to find out the equation for x bar np. So try doing this. This was the main equation. Just try finding out those individual terms and then I think you'll be able to do it. So let's try doing this. Okay, so for the wing, you write Cm as, let me Cm wing. Okay, so Cm of the wing is written as Cm AC of the wing plus x bar Cg. I'm writing in terms of Cl, okay, because we need to find out d sigma bond dCl. X bar AC, Cg minus x bar AC of the wing into Cl, which gives dCm by dCl of the wing as x bar Cg minus x bar AC wing. Okay, similarly now let's do it for tail. So Cm of the tail in terms of, like, in relation to the Cl. Okay, so you get Cm naught minus Vh eta 1 minus dou epsilon by dou alpha into Cl alpha tail, right? What term is missing here? Yeah, so in terms of, so it will be alpha wing. Now if I do dCm by dCl of the tail, you get minus Vh eta 1, it's not Cl of the tail, it's dCm by dCl component of the tail. Okay, 1 minus dou epsilon by dou alpha Cl alpha tail by Cl alpha wing. Okay, now let's do it for the fuselage. It's just that component. We haven't studied any expansion, so it's just dCm by dCl of the fuselage. Even in the options it is given in that manner, right? So now just put it all together. Just put it in the equation x bar np. I'm taking Cg on the other side because we need to find out np. So you have x bar Cg, and then you add all these individual terms, that is this one, this one. So you have minus x bar Cg plus x bar AC wing, then you have plus Vh eta 1 minus dou epsilon by dou alpha Cl alpha of the tail, Cl alpha of the wing, minus dCm by dCl of the fuselage. So this in this get chopped off, and this is the final answer. X bar np in terms of dCm by dCl. So from the options, what do you get? So which is the right answer? You have negative of this. The first answer is the right answer. Okay. So even if there are other components like canard and all of that, just go on adding to this thing. You have dCm by dCl of the canard, so on and so forth. Each component, just keep adding it. The negative of the slope, you just add it to get the overall slope. Alright, let's go to the next question. If an aircraft continues to go further away from equilibrium position after being disturbed, then the aircraft is called, oh, it hasn't loaded. Okay. If the aircraft continues to go further away from equilibrium point after being disturbed, then the aircraft is called, very simple. We studied this when we started stability, right? Unstable. So I think the example that was taken was of a ball in a bowl, right? So this is when you push the ball, it oscillates and comes back to its equilibrium position. So this is statically stable. Then you have an upturned ball, and you put the ball there. And if you push the ball from its position, it goes further and further away from the equilibrium point. So this is unstable. And then you have a flat surface, and then you place the ball and you push it. It stops at its new location. So it is stable at its new location. That is called neutrally stable. So these are the three categories. So if the aircraft continues to go away from equilibrium position after being disturbed, it is this unstable case. Alright, very simple. Next, it hasn't loaded now. A wing alone aircraft has aerodynamic center pitching moment coefficient as minus 0.096. If lift coefficient at zero angle of attack CL naught is 0.28, find Cm naught. Consider XCG as 0.35 and assume aerodynamic center as 25% of mean aerodynamic chord. Okay. So what they've asked you to find? What have they asked you to find? They've asked you to find Cm naught, given all the other terms. Now let's try doing this. The equation was Cm is Cm naught plus Cm alpha into alpha. So just try doing this. We need to find out Cm naught with the terms that are given to you. Try doing it. Minus 0.068. Let's just try solving it and see if it's the right answer. Okay, so here let's just expand this. So you have Cm naught here in this case is nothing but CMAC. It's the wing alone configuration. CMAC, which is given here, plus you have CL. You need to write it in terms of CL. So what happens is you write after expanding it further. Okay, so it's CL naught into x bar CG minus x bar AC plus CL uh, alpha into x bar CG minus x bar AC. Okay, so now just expand it. We need to find out Cm naught. So this entire thing would come under Cm naught because those are the terms that are independent of angle of attack. So Cm AC is minus 0.096. So I'm just writing Cm naught. Okay, plus CL naught is 0.28 and x bar CG is 0.35 and x bar AC is given as 25% of mean aerodynamic chord, so minus 0.25. Okay, so then what do you get? So it is minus 0.068. Okay, so that is the right answer. Okay, let's move on to the next question. An aircraft is said to be statically stable if it has in, just look at the options and try telling me. By definition, this is very simple. Initial tendency to come back to equilibrium or condition after being disturbed. It has a tendency to return to equilibrium state with the help of pilot's input. It has more lift than weight always. It has more thrust than drag. Option A, correct. So the pilot's input is nothing but control, and we have discussed that the control has no effect on static stability in any way. Okay. Okay, next question. Longitudinal stability means stability about yawing axis, lateral axis, pitching axis, or negative yawing axis. Which is it? Longitudinal stability is what we've been discussing all this while, right? So is it about yawing axis, lateral axis, pitching axis, or about the negative yawing axis? It's about the pitching axis, right? So you're taking Cm, pitching moment coefficient, so it's about the pitching axis. Okay. Now let's look at the next question. An aircraft wing is experiencing an angle of attack of 5.21 degrees. If downwash due to wing is 2.62 degrees, then how much angle is seen by the tail of the aircraft? Very simple. We've done this during the derivation of neutral point and stability. Just quickly find out this. 2.59 degrees, correct. So the angle of attack seen by the tail is angle of attack of the wing minus downwash, right? And if there were other components included, so if you have a tail setting angle, it will just be plus I tail, which is not here in this case. So it's just angle of attack of the wing, which is 5.21 degrees, minus downwash is 2.62. So yes, 2.59. Next question. A positive tail incidence angle setting as compared to zero tail incidence angle setting will result in less static stability, more static stability, same static stability, none of these. So this is IT, okay. So what is the right answer? A, less static stability. Why would you say that? So let's just look at the tail contribution equation. Where was it? Yeah. So this was the equation. Look where IT is featuring. And IT features in Cm naught of the tail, correct? And Cm naught does not contribute towards stability in any way, correct? The only contribution is, only necessary requirement is the slope. So IT only comes in the Cm naught tail part, right? This one, this term. IT doesn't feature anywhere else. So IT doesn't affect the stability in any way. Yes? Okay. So when you deflect, when you have a different tail setting angle, let's just go to that question. Yeah. So positive, negative, zero tail setting angle, none of them affect the static stability. So it retains same static stability. That's the right answer. Okay. So just try to remember those equations, at least those terms. Just try to remember it. Okay. What all feature in Cm alpha, what all feature in Cm naught. Okay. For an aircraft, the Cm versus CL plot is shown in figure. Is shown in the figure. The center of gravity is at x bar CG is 0.28. What is the neutral point of this aircraft? Very simple, right? You try doing this. So let's try doing this. So your static margin is nothing but x bar np minus x bar cg. That's also equal to minus dCm by dCl. And they've asked you to find out neutral point when they've given you Cg. So just rearrange this equation and then you have x bar Np is x bar Cg minus of the slope. Okay, so minus, what is the slope in this case? 0.078 by 0.65. And you can just take 2 points. So this is 0.1, 0.2, and then you can find the slope. So here it is 0.28 plus this quantity, which comes to 0.12, and the final answer is 0.4. Okay, so neutral point is 0.4. Okay, next question. Just read the data given to you in this question, then we'll answer a series of questions based on this data. So the wing fuselage pitching moment characteristics of an airplane is given as, you have the equation for that, you have the Cm naught, Cm alpha for the wing fuselage combination, okay, where alpha is the fuselage reference line angle of attack in degrees, VFS means the wing fuselage combination, and WFS. So SW is 16.53 meters square, the span is given, the mean aerodynamic chord of the wing is given, so x bar Cg is given, aspect ratio of the wing, then you have CL alpha of the wing fuselage combination in per degrees, wing setting angle, you have CL at alpha equal to 0, that is nothing but CL naught. So this is CL naught. Then you have horizontal tail data, the moment arm, the aspect ratio, the tail efficiency factor, and CL alpha of the tail in per degrees. Okay. Now let's look at the questions. So this is the same data that is given. Okay. It is desired to have the complete airplane pitching moment characteristics as, so the Cm pitching moment characteristics of the entire, so that's the wing, fuselage, tail, the entire combination, we desire it to be 0.15 minus 0.025 alpha. So what is the contribution of horizontal tail towards Cm naught tail? Cm naught tail, that's what they asked. Contribution of so contribution of tail towards Cm naught. So you have, this is Cm naught, this is Cm alpha. They've asked you what is the contribution of just the tail towards this pitching moment characteristics. Just take a minute and try doing it. This is also fairly simple. So let's do this. It's just the subtraction of the two components, right? So from this, you subtract that from this entire thing. So that is Cm naught contribution is 0.15 of the entire thing. Cm naught of wing fuselage alone is minus 0.05. So Cm naught of the tail is 0.15 minus of minus 0.05, which is nothing but 0.2. Correct? So that is the contribution of tail towards Cm naught. Now next question. What is the contribution of horizontal tail towards Cm alpha? Let's taking some time to load. Along similar lines, what is the contribution towards CM alpha of the tail? In per degrees, okay? So it's along similar lines. So CM alpha of the tail they've asked. So it is CM alpha of wing fuselage tail minus CM alpha of wing fuselage. Okay, it was here. It's minus 0.025 minus 0.025 minus this is 0.0035. This comes to minus 0.0215. Right? So that is the right answer. Let's go to the next question. The approximate value of, it's taking a while to load here, the approximate value of dou epsilon by dou alpha, where epsilon is downwash. So we had seen this formula in one of the initial slides. Try recalling that and check the units. Try doing it and we'll do this together. It's a direct application of the formula. Okay, so 0.35 he says. Let's try doing this. So d epsilon by d alpha was 2cl alpha of the wing by pi e ar, again a of the wing. So 2cl alpha of the wing is given by, where is it, of the wing fuselage. So it's 0.07 by pi. E is not given, take it as 1. Aspect ratio is 7.3. And here this is given in per degree, so you need to convert it to per radians. Okay, so that is 180 by pi. And when you do all the calculations, you get 0.35. Yes, you're right. That's absolutely right. Let's go to the next question. So the thing that you need to remember here is this 180 by pi. These equations are valid only if it's per radians and radians on either side. Okay. Next question. The tail volume ratio of the horizontal tail. VH. How do you find this? Oops, it's taking a while to load. I'm really sorry about that. Okay. The tail volume ratio of the horizontal tail, VH, is. How do you find this? This is a little different. Just try doing it. Try thinking about it. And we'll do it together. Just try. let's look into this. So VH, the usual that we have, 0.453. Okay. Usual formula that we have is STLT by S into C. So we don't have those quantities here with us. So what do? We take the horizontal contribution of tail towards Cm alpha. So that is Cm alpha of the tail. What is the formula? It is minus eta VH Cl alpha tail 1 minus dou epsilon by dou alpha into, this is the formula. Okay, so do we have these terms? Yes, we've calculated all of these, or they're given to you. So efficiency factor is 1, VH is what we need to find out. Cm alpha tail is, how much did we get that as? 0.0215. Cl alpha of the tail is 0.073. Here, since both of them are in per degrees, you can leave it as such. Okay, and 1 minus dou epsilon by dou alpha is a unitless parameter, right? So it's dimensionless. So it's 0.35. And when you substitute all these, you get VHS 0.453. Correct, you're absolutely right. Alright, let's go to the next question. The ratio of horizontal tail area to wing area, ST upon S. Now that you have calculated VH, you should be able to ratio of horizontal tail area to wing area. Now that you've calculated VH, you should be able to calculate ST upon S. This should be very simple. You said 0.153. Yes, that's right. So let's just write it down for the sake of completion. So VH is ST LT to C bar. Can you mute yourself? Okay. So yeah, we need to find out ST upon S. VH we found as 0.453. So you have VH C bar by LT. VH is 0.453. C bar is 1.524. LT, where was it here? 4.496, and then yes, it's 0.153. Correct. Let's go to the next question. The approximate value of epsilon naught in degrees is, again, direct substitution of the formula, keeping in mind the units. Let's try doing it. 1.3, let's try doing it. Epsilon naught is, what was the formula? 2Cl naught. 2Cl naught by pi E AR. So 2 into Cl naught was, why was Cl naught? 0.26 by pi. E is not given to you, 1. Aspect ratio is 7.3, and then you get, this is in radians, okay, so you get 0.22 radians. When you convert it to degrees, you get 1.3 degrees. Perfect, right. Next question. Calculate the tail incidence angle in degree required to achieve Cm naught tail. Calculate the tail incidence angle IT in degree required to achieve Cm naught tail. We had seen that IT only features in the Cm naught tail. So just write the Cm naught tail, it's a component of tail, component of Cm naught, contribution of Cm naught by the tail. Just write down this equation and then you'll be able to find out IT. And then you'll be able to write it. So it was VH eta Cl alpha tail and then the angle, right? So that was, it was alpha tail. Just substitute alpha tail and you'll be able to get it. Okay, so it's not the entire alpha tail. I think I made a mistake here. Let me just fix that. So it's the terms of alpha tail that do not depend on angle of attack of wing. Okay, so it's this, not the entire alpha tail. So it will be I wing. In this case, you have a wing setting angle, and then you have epsilon naught minus I tail. Yeah, try doing it now. Just check the signs. Let me just verify the signs. Just give me a minute. I'm not very sure about the, have we made a mistake with the signs? I wing plus epsilon naught minus I tail. Okay, that's right. Yeah. So we had calculated the epsilon naught value, right? So you should be able to do it. Just substitute. We just calculated epsilon naught in the previous question. Just substitute that value. Minus 2.7. Okay, let's look into it. So Cm naught, so let me just write it. Cm naught of the tail was, oops, why is this not working? Yeah, so Cm naught of the tail was 0.2. 0.2 and VH was 0.153. Efficiency factor is 1. CL alpha tail is 0.073. I wing is 2 plus epsilon naught in degrees is 1.3. So this is in per degrees, but all of your the angles are also in degrees. So, and you're required to find out also in degrees. So when you substitute all of this, you get I tail to be minus 2.7. Correct. So it's a negative tail incidence angle. Okay, now this was the set of questions that we had to deal with the given data. So what can you say about the overall stability of the aircraft? Is it stable or unstable? Of this aircraft that we just solved, is it stable, unstable, neutrally stable? What is it? Stable. Why? Because your Cm alpha, the overall Cm alpha is negative. That is the only thing that we have to check. This Cm alpha is negative. And I think in the next question we had seen the contribution of tail towards Cm alpha. Again, it's a negative quantity, right? So there again, this is corresponding to what we had just seen. So yeah, contribution of tail towards static stability is negative, so it contributes towards stability. What else can we understand from this set of data? That's it. Okay, let's move on to the next question. Okay, now you have another set of data given to you and then some questions based on that. So here you have the weight of the aircraft, cruise velocity, the area, surface area, the density at cruise altitude, you have aspect ratio, you have the CG and AC at the same point. Then you have neutral point, then you have some data related to stability and all the other parameters. you have CMAC, you have CL alpha wing and CL alpha tail to be the same, so you have the same airfoil. You have angle of attack at 0 lift to be -2, wing setting angle, tail setting angle, tail efficiency factor, horizontal tail volume ratio, Oswald's efficiency factor, control surface effectiveness parameter, and maximum deflection of elevator. Okay, now let's look at the questions. Lift coefficient for cruise is, it's fairly simple, right? So we've been doing this for a while now. So what is the lift coefficient for cruise? For cruise, the condition is lift equals weight, and they've asked you to find out coefficient of lift for this condition. Just find out quickly. It's very simple, right? So you just have to write the lift equation is half rho v square SCL and lift equal to weight. So it's this. So CL is 2W by rho v square S. You substitute the value, so it's 2 into 2500, 9.81. By density is 0.85. Velocity is 130 and S is given 60. You substitute all of these values, you get 0.569. So that is the right answer. Next one, the downwash angle at tail epsilon naught is approximately, hasn't loaded, okay, epsilon naught in degrees, approximate value of epsilon naught in degrees. Again, you know the formula, direct substitution. Try to find that out. the formula was epsilon naught is 2 CL naught by pi EAR. What do you not have here? CL naught. Try to find that out. So how do you find out CL naught? You make the graph first. So CL versus alpha. CL naught is this value, right? So that is your CL naught. This is your angle of attack at 0 lift. You have the slope, you have 2 points, you can find out CL naught, correct? So CL naught is, what is the value? Angle of attack is 2 into what is the slope? 4.584, that is in per radians. You just convert it and then you get pi by 180. What do you get? You get 0.16. They've asked you in degrees, that's why I have done this, okay? The answer is required to be in degrees, that's why I have multiplied the pi by 180. Now just substitute it here. You get 2 into 0.16 by pi. E is 1, AR is, which is AR 5. What do you get? You get 1.16 degrees. Correct? Okay. Let's go to the next question. The value of Cm naught of the aircraft is. Assume Cm naught of the fuselage is 0, contribution of fuselage is 0. Just assume that. That's not required here. Cm naught contribution of the aircraft. Value of Cm naught of the aircraft. So you need to find out Cm naught of the wing, Cm naught of the tail. So Cm naught is what they've asked you to find out. So it is Cm naught of the wing plus Cm naught of the tail. So find out those two quantities individually, add them. Cm naught of the wing is equal to Cm naught of the tail is equal to. Tail, we just wrote down the formula for the previous question. It was VH CL alpha tail I wing plus epsilon naught minus I tail. Similarly, what was for the wing? It was CMAC of the wing. Then you had the CL naught contribution, CL naught x bar CG minus x bar AC wing. Okay, just try doing it now. Okay, let's just quickly substitute the values and find this out. CMAC of the wing is minus 0.1 plus CL naught we found out in the previous thing, it's 0.16. X bar CG minus X bar AC, 0. So this comes to minus 0.1 because your CG and AC are the same point. Here, tail efficiency factor is 0.8, volume is 0.45, CL alpha of the tail is 4.584, and we're taking everything in degrees, so pi by 180. Wing setting angle is 3 plus epsilon naught we found it in the previous question, 1.16. Tail setting angle minus of 2 degrees, so 2. You get this as 0.1774. Add both of them, you get 0.1 plus 0.1774, you get 0.0774. So here you can see that you can trim the aircraft at a positive angle of attack because the CM naught is positive. Next question. Static margin during cruise is close to. You have both the values. Static margin is x bar NP minus x bar CG. So both the values are just given to you directly in the question. 0.52 minus 0.3. So you get 0.02. 0.22. Right? Next question, value of Cm delta E in per radians is close to. So the formula for Cm delta E we had seen in the control slide. So Cm delta E, this is a direct substitution of the formula, okay. So it's eta Vh Cl alpha tail into tau. What is tau? What is tau? What is it called? So it's the control surface effectiveness parameter, okay. In this case, elevator effectiveness parameter. Okay, just substitute the values and quickly tell me the value. Yes, substitute the values and you get 0.66. Perfect. Next question. For cruise flight, delta E required to trim the aircraft is approximately delta E trim. What is the formula for delta E trim? Delta E naught plus d delta E by d Cl into Cl trim. Right? And if you expand this, what was it? It's minus Cm naught by Cm delta E plus x bar np minus x bar cg by Cm delta E into Cl trim. Try doing this. Again, you have all the terms, all the quantities, just do it. Substitute the terms. So Cm naught was what? We had calculated this, right? Naught 0.000774. 774. Cm delta is minus 0.66 plus x bar np minus x bar cg. Again, we've done this 0.22. 0.22 by minus 0.66 to Cl trim value, we had calculated CL initially for cruise. Cruise in this case is trim, right? CL trim is 0.569. So what value do you get here? You get minus 0.0723 radians, and you convert it into degrees, you get minus 4.143 degrees. So you deflect the elevator up or down? Down. We had seen that downward elevator deflection is considered positive, right? So in this case, we've got minus 4.143 degrees. So you deflect the elevator upwards. Our convention is that we'll deflect the elevator down is considered positive. Where was it? We had seen this in the control slide, I think. Yeah. So elevator down is considered positive. So we've got a minus 0.4143 degrees. So that is upward deflection of the elevator. Okay. So with this, we come to an end of today's session. Do you have any questions? Okay, if there aren't any questions, we'll end the session here. We'll meet again on next week to discuss the assignment 9. Thank you. Thank you.